We're going to be looking at the graphs of cubics and higher order, so bigger than cubics. And a lot of these graphs, including, I suppose, our quadratics as well in this, follow kind of particular rules and particular ideas to do with both the roots and the shape. So those are the two things we're going to be focusing on. We're going to be looking at kind of what do the roots tell me about the shape of my graph, and what do they tell me about if I was sketching my graph, how can I kind of know what my graph's going to look like, and all that sort of thing, and how can I kind of work this out from the equation I'm given or from the information that I'm given. And it's important that you are able to kind of engage with and kind of use all that information and synthesize that to be able to sketch the graph, or to be able to work out what a graph would look like, or to be able to recognize a graph if you're given different pieces of information about it. This is going to help you in particular questions, but it's also obviously going to help you to answer particular types of questions that you could be asked. So starting off with the roots, first of all, for any given polynomial, any polynomial at all, the maximum number of distinct roots, remember distinct root just means different, so the maximum number of different roots that a polynomial can have is the same as its degree. So we already know, say a quadratic is an x squared, it has a degree of 2, and it can have a maximum of 2 different roots. A cubic could have 3 distinct roots. Power 4 would have a maximum of 4 distinct roots. And we can talk about what we call the root behavior, so how the graph behaves at its different roots. So if a graph has distinct real roots, so all different real roots, the graph will cross the x-axis at these distinct real roots. So looking at the example we have here, kind of zooming in there to make it a bit clearer. So we can see that it has 3 roots there. It has one root at -5, one at -2, and one at 3. And it is crossing the x-axis at each of those points. So we can see very clearly the 3 distinct roots that I have there. If we have complex roots or no real roots, so the kind of complete opposite of my distinct real roots, at complex roots, the graph will not touch or cross the x-axis. It won't even go near it. So we can see here, this graph is kind of sitting in midair, and there's a good bit of distance between the kind of bottom of the graph and the x-axis. So it doesn't actually touch the x-axis at all. And that just tells us that there are no real roots. So if you think about what a root means, that is kind of the zero of the equation. It's generally where it crosses the x-axis. But we know from complex numbers and things like that that we could have equations and quadratics that would have just complex roots, that would have only complex solutions. So that's kind of what that would look like in terms of a graph. It kind of sits up in midair, doesn't go near the x-axis at all. If we have real roots, we have 2 particular things we're going to look at within that. And that comes down to a thing called the multiplicity. So I'm going to just focus on this note first of all, and then we'll go through the meaning. But the multiplicity of a repeated root is the number of times that the root is repeated. So the number of times the root is repeated. So if I have, say, my quadratic there, a quadratic has 2 real roots. A quadratic like this has a repeated root, which means it must be repeated twice. So it could be written as, for example, x minus 3 all squared. And there the multiplicity is the 2. It tells us that this root is repeated twice. So it helps us to see how many times the graph is repeated. With a repeated real root, we know that it can either be repeated an even or an odd number of times. So that's fairly self-explanatory. The power can either be even or odd. It kind of has to be one or the other. If it is even, the graph will touch but not cross the x-axis. So we saw that with the quadratic there. The quadratic comes down, it touches the x-axis, and then it continues back on. It doesn't go through it at all. If the multiplicity is odd, so for example with this cubic in the question here, if the multiplicity was, say the root is repeated 3 times, then the graph is going to kind of touch and cross the x-axis at that point. So we get this kind of interesting behavior where it nearly lies flat at the x-axis there. Okay, and what that means, if I was to give you the equation of this cubic, it's actually x minus 2 cubed. So the multiplicity there is odd. Okay, the multiplicity is odd. God, it's all going wrong. So my multiplicity here is odd because it's 3. And that just means that my graph is going to lie flat at that point. Now we will have graphs, obviously, when we get into bigger powers where we could have a combination of these things. So we might have some graphs where they touch the x-axis at one point, so it's repeated maybe an even number of times. We could have it crossing the x-axis at another point. And it's important that we kind of understand what it means when we see these graphs. So a lot of this kind of section and this is being able to interpret the graphs. Okay, working from the graphs to kind of write down the equation, but then also if we're given the equation, can we kind of sketch roughly what the graph would look like without actually plotting the points? So it's important that you kind of have a sense of what this root behavior means. So again, just comes down to the three different types of root behavior. We have either distinct real roots where it crosses through the x-axis, complex roots where it doesn't even touch the x-axis, or repeated real roots. And for the repeated, we have to just remember to look at the multiplicity. So if the multiplicity is even, if the root is repeated an even number of times, then the graph is going to touch the x-axis there. If it's repeated an odd number of times, it will kind of lie flat. It will touch and cross, if you like. So it kind of does cross over, but it doesn't just cross straight through. It kind of lies flat at that point. Okay, having looked a bit about the roots there, we wanted to also talk about the shape of the graphs. Okay, so when we talk about the shape of a graph, we're just talking about kind of what does it look like in terms of maybe the arms of the graph. So the arms mean kind of the two end points as far as we've drawn, and maybe how does the rest of the graph behave? So are the arms pointing the same way? Which arms pointing up? Which arms pointing down? How does that relate to everything else that's going on with that polynomial? And obviously depending on what the equation of the polynomial is. So the important thing is just that we need to know what a polynomial tells us about the shape. And as I say here, we're particularly interested in describing the arms. So looking at the kind of examples here, if we just jump ahead, when we talk about the arms, we're just talking about these parts here. So kind of the end behavior, sometimes you'll hear it called as well. So the end behavior of the function as we continue towards, say, infinity, so to a kind of infinite positive value, or to an infinite negative value. What happens with my function? Which way is it going? So the note I've put here is very important as well. There are infinitely many polynomials that share the same roots. So there could be any number of polynomials that would have the same roots, but their graphs would look slightly different. And this is most notable at something like the y-intercept. Okay, that's always a good point for us to look if we want to see how the shape is going to be different. But we can also see it just in different points within the graph. So we know, say if we think of like quadratics that we've done before, we know that we can have multiple different quadratic equations that would have the same roots, but the actual equations themselves would be different. And it's important just that we have that distinction where with a polynomial, we're kind of talking about functions. And if a function has a different equation, has a factor of 3 or a factor of 4 or something for each term, that is considered a different function. If we had it as equations, we might just divide across and we might say it's just the same equation. But in terms of functions, each of those functions is considered to be distinct. So it's important, again, that we just have that little distinction in our head and are kind of prepared for it. And we're going to see that a little bit later then when we're looking at kind of writing down the equation of the polynomial. But the main thing with the shape is we're going to be looking at the degree and we're going to be looking at the leading coefficient of my polynomial. So starting with the degree, we know the degree is the highest power of the variable. So the degree is the highest power of the variable. And the degree tells us about the arms of my function. So if the degree is even, that means that both arms either point up or both arms point down. Okay, and what we really mean there is just they point in the same direction. So if my degree of my polynomial is even, both arms will point in the same direction. And I've drawn a power of 4 there, but you could think about a quadratic. A quadratic has a power of 2 and both arms either point up, or if it's a negative quadratic, both arms would point downwards. So they both point in the same direction. If the degree is odd, we would say that one arm points up and one arm points down. We have the example here of a cubic. So we can see one of the arms here is pointing down and the other arm is pointing up. And we could easily have the same cubic going the opposite way with one arm pointing down and one arm pointing up then also. So the degree there tells us immediately whether both arms are pointing the same way or not, but we also would want to know, well, which way are they going to be pointing? So it's one thing to know that yes, they're both pointing the same way, or they're both pointing different ways, but particularly if they're pointing different ways, is it one up, one down? Which one is up, which one is down? If they're both pointing the same way, is it up or down? And to know that, we need to look at the leading coefficient. And the leading coefficient is the coefficient of the highest power. So it's the coefficient of the term with the highest power. So in terms of our quadratics, that would be your coefficient of x squared. And we already know that with your coefficient of x squared, if that was positive, my x squared graph goes up like this. If my x squared, if it's minus x squared, my graph's going to be n-shaped or negative, so they both point down. And that actually is kind of the rule that we're looking at. If the leading coefficient is positive, we say that the right arm points up. Okay? If the leading coefficient is positive, the right arm points up. If the leading coefficient is negative, then the right arm points down. So we're always kind of looking at the end behavior, the second arm there. And then we can use the degree to kind of surmise what's happening to the first arm, to the left arm. So if the degree is odd and we know that the leading coefficient is positive, then that means the right arm points up, and if it's odd, that must mean that the left arm points down. And similarly then, if the leading coefficient is negative, then the right arm's going to point down, which if it was odd would mean that the left arm would have to point up. If we have an even degree, then both arms are pointing the same way, and in this case it might be that they're both pointing down, for example, if the leading coefficient was negative. So let's have a look at how that actually helps us with drawing sketches of the graphs, because it's all well and good to kind of talk about the theory and to talk about all this idea, but it's going to help us a lot more if we can kind of look at sketches and look at how we kind of bring all this idea together. So we're going to start by looking at f of x here. So immediately looking at f of x, I can see that it looks like I have, say, 3 different roots here, but I can also note that one of my roots is squared. So that actually means that I have a total of 4 roots. So a total of 4 roots means that my degree is 4. So the degree of my polynomial is going to be 4. Okay, so if we want, we can just rewrite those. So at the minute, those are factors, but to rewrite them as roots, kind of using our factor theorem from before, I can rewrite those fairly easily. So minus 2, 1, 1, and 4. So it's a repeated root at 1 and distinct roots at 2, at minus 2 and 4. The degree of the polynomial is 4. So the degree 4 tells me the behavior of the arms. So both arms are pointing in the same direction. So because the degree is 4, both arms are going to either be pointing up or both arms are going to be pointing down. To know whether they're pointing up or down, we need to kind of be able to look at the leading coefficient. And if I look at my different roots that I have here, I have x multiplied by x multiplied by x multiplied by x, and I would end up with x to the power of 4, and it would be positive because there's nowhere there where I can end up with a negative. Okay, if we had a negative on the outside, for example, then I would know that the leading coefficient is going to be negative, but my leading coefficient here is going to be positive. Okay, my leading coefficient is going to be positive. Leading coefficient positive means the right arm is pointing up. It means the right arm is pointing up. Because the degree is 4, that actually means that both arms are going to be pointing up. So we can kind of already move towards a little bit of a sketch of this graph, and it is just a sketch. Okay, it is just a bit of a sketch. It doesn't have to be the most accurate thing. We will obviously be looking at drawing much more accurate graphs. So looking at my roots, we're going to mark those in first. So my graph has to cross at minus 2, it has to cross at 4, and it is going to touch at 1. It's not going to cross at 1, it's only going to touch because it's a repeated root with a multiplicity of 2. Okay, a multiplicity of 2. So that means that it's only going to touch the x-axis at that point. I know that both arms are pointing in the same direction and they're both pointing up, so that tells me that my graph starts up, goes down through my root of -2 here, goes up to my 1, and goes back down again, and goes up through 4. Okay, so I end up with a nice sketch of a graph. Obviously, as I say, it is just a sketch. We haven't even filled any y values here at all. In some cases, they may give us some kind of maximum or minimum values that would help us with kind of these points here on my graph. But for the minute, we're just kind of doing a little bit of a sketch, filling in my roots and drawing everything else in as best I can with the information presented to me. So just make sure when you're going through here that you can kind of see where we're pulling all of this information from. And if you're a bit unsure, then maybe just go back to when we kind of talked about that little section or whatever part it is that is maybe catching you out. So let's look at the next example here. So first of all, we're looking at the factors that I have in front of me. And if I want to rewrite those factors as roots, I get x equals 3, x equals 2, and I get x equals -5. But this x equals -5 is repeated 3 times. Okay, so it has a multiplicity of 3. So immediately I know that's going to lie flat at x equals to -5. Because it has an odd multiplicity, the graph's just going to kind of sit there and then continue on its way. The other two roots, distinct roots, it's just going to cut through at those points. Looking at the degree then, we have a total of 5 roots. So I have my 2 distinct roots and then my root that's repeated 3 times. So a total of 5 tells me that the arms are pointing in different directions. So because they have a degree of 5, which is odd, that means the arms are pointing in different directions. I need to look at my leading coefficient, and I can see with this question, we can have what I was talking about in the previous one. We're starting with a minus in front here, which means that my leading coefficient is going to be negative. When I would expand my brackets there, I would end up with -1 x to the power of 5. So my leading coefficient is negative. That means my right arm is going downwards. Okay, my right arm, I'm going to end on a decreasing idea. So I feel like I've gathered as much information as I can here from the polynomial. So let's just sketch some of this out. Just looking as well at what points I need to include. So 1, 2, 3, -1, -2, -3, -4, -5. I'll put in a -6 as well. Okay, so we know first of all that I'm going to cross the axis at 2 and at 3. And then I'm going to touch the axis or lie flat at my -5. I know that the graph is going to be going downwards from this point, so I'm actually going to start down here because I know what's happening at that point. I'm going to go down again, okay, go up to my -5, and here's where I need to just be careful. I need to lie flat at that point. I'm going to go back over here because I made a bit of a mistake there, so let's go, and then I'm continuing onwards. So we're showing that our graph is lying flat at -5, so we can see that here. So lying flat at -5, but at the other two roots just crossing through as normal. So here we have our repeated root. So here we have our repeated root repeated 3 times, and then I have my 2 distinct roots at the other 2 points. Okay, so just kind of using all the information that's presented to us there as best we can in order to help us to kind of answer these questions. Let's look at an exam question here. So from 2014, the graph of a cubic function cuts the x-axis at x equals -3, x equals -1, and x equals 2. So those are going to be my roots, and it cuts the y-axis at 0, -6. Cuts the y-axis at 0, -6. So taking all that information in with me, I need to sketch a graph of the function. So if I write down over here some key points, I know it's degree 3 because it's a cubic function. Okay, I know it's degree 3. That's going to mean 1 arm up and 1 down. Okay, looking at my roots there, if I was to multiply all of that out, I'm kind of expecting that I would get a positive degree. Okay, I'm kind of expecting that I would get a positive degree. Now I can't be absolutely certain, but I'm kind of anticipating that I get a positive degree. And I know that it cuts the y-axis at 0 minus 6. Okay, it cuts the y-axis at 0 minus 6. So let's just kind of plot all those points, see if that kind of makes things any way clearer for us at all. So just using as much space as I can here. So minus 1, minus 2, minus 3, 1, 2, 3, 4. Okay, minus 1, minus 2, minus 3. Do you know what? I'll go up in 2's on this axis here. So minus 2, minus 4, minus 6. Okay, so my graph has to cut through this point. It also has to go through minus 3, minus 1, and 2. Okay, I know that one arm is going up, I know that one arm is going down. So in order for that to happen, we can kind of see that my graph has to be decreasing here in order to go down to the minus 6, which means it then has to increase to go up to this 2 point here. And therefore we'll have to start by going downwards. So again, I'm kind of using a little bit more of the information that's presented to me there to help me to see what's going to be happening. So I know between those two roots it has to go down to minus 6. There's no way it could be kind of coming in the other direction there. Okay, so just kind of helping ourselves to see exactly what's happening. We know that between minus 1 and 2 it has to be down below the x-axis if it's going to hit the minus 6. So that just helps us to see which arm is going which direction. Now the reason that I'm being quite particular, say in this case, is that we haven't been given the exact polynomial. Okay, and that's what they're asking us about in the second part here, is verify that it can be written in this particular form. And the reason I'm kind of being quite particular here, and it's something we're going to look at in the second section, is they've given us a point that the graph has to go through. So say for example I take my three roots and I rewrite them as factors. That would be x plus 3, x plus 1, and x minus 2. And if I was to multiply that out, so let's multiply one at a time. So x squared minus x minus 2, and I get x cubed minus x squared minus 2x plus 3x squared minus 3x minus 6, and simplifying x cubed plus 2x squared minus 5x minus 6. Yeah, minus 5x minus 6. Okay, so we have the polynomial here, and it is matching up with the polynomial that we have in the question. But the key thing we have to be careful of is that we know it goes through this particular point, and this is what I was touching on earlier, and it's what we're going to touch on in a second as well. So to verify that this is the exact function that I have, well, one thing we could do is use the point that we have. So we know that for this function, f of 0 is equal to minus 6. So if I'm to sub in 0 into my function, just to verify for myself, I get 0 minus 6, which is minus 6 as expected. And therefore we can say that f of x can be written in this form. But what we're going to see is that in general, we have to include an extra little part just to ensure that the function we're getting is the exact function that's been plotted. Okay, and it's kind of leading us nicely into this next little part here. So as we've seen now, we can use the shape, we can use the roots, we can use all of that to help us to find an expression from a polynomial from the graph, and also to graph it if we're given the expression. But we've also seen, or we should know, we've kind of said that there are infinitely many polynomials that share the same roots. Okay, as I kind of touched on earlier, unlike equations, we consider each of these to be distinct or to be different. And therefore, when we are trying to find the expression for a polynomial, we must include a constant term. We must include a constant term. It's kind of an amplification term, if you like. It's an amplification term, and then we will use a point on the graph to find the value of that constant. And where this all comes down to is if you think about, say, a cubic graph like this. that goes through these 3 points. And say I call this f of x. I could draw another cubic graph going through those same 3 points, but that maybe goes higher and that goes lower than the one that I have here. So it goes through the same 3 points, but it goes higher and goes lower. It reaches higher points. It reaches kind of bigger maximums. The same thing I could do as well. I could have another function that maybe doesn't even go as high, takes a smaller approach, but reaches the same roots. And I can have infinitely many number of those functions. Okay, infinitely many functions. I could even have a function sharing the same roots, but which is actually moving in an opposite direction, which is in a completely, it has a different leading coefficient, has a negative leading coefficient instead of positive. So in order to be sure of the graph that I have to include an extra constant term. And that constant term is tied to kind of my leading coefficient and my amplification of the function. And we're going to see that in these examples here. It's kind of the best way for us to just jump into it. So looking at this graph on the left-hand side, so the numbers are a little bit small there, but we'll just kind of bear with it. So I have 3 roots that I can see straight away. So one of my roots is x is equal to -3, another root at x is equal to -1, and a last root at x is equal to 2. And I can see also that I have a point 0, -6 that I know is on the graph. So what I'm first going to do is I'm going to rewrite these as factors. And x minus 2. I'm going to then multiply out these brackets here. So x squared minus x minus 2, x cubed minus x squared minus 2x plus 3x squared minus 3x minus 6. I get x cubed plus 2x squared minus 5x minus 6. Which I think is the same quadratic that I had in the last one. But it's fine, it doesn't matter. Okay, same quadratic I had in the last one, it's all good. So we're looking at the equation, writing the expression for this polynomial here. So this is like a general equation. Okay, this is like a general equation for a polynomial that has these roots. So if you like, this is a polynomial. We don't want a polynomial. We don't want a polynomial. We want the polynomial. We want the polynomial that's in the graph. So this is a polynomial. I want the polynomial. So in order to be sure of that, I'm going to include an a term. Okay, because it's a polynomial, I'm going to include an a factor. And this, now, I'm happy to say that's f of x. Okay, so f of x is this term here, including my a kind of constant factor there. So to help me find the value of a, what I'm going to do is I'm going to use a point that I know. And I know that f of 0 is equal to -6. So I'm going to sub in f of 0. So 0 plus 2 times 0 minus 5 times 0 minus 6. So again, I get that, and we know it's equal to -6. So I get that a times -6 is equal to -6, which just means that a is equal to 1. So my function f of x is the same as we had in the last question, 2x squared minus 5x minus 6. Okay, nice little function for us there. So in this case, the amplification factor just ends up being 1, but it's important that we have checked that we have kind of attempted to verify that one. So let's look at the next example. So again, we have a root at -1, we have a root at 1, and we have a repeated root at 2. So I'm kind of content to say here that g of x is going to be, if I include my amplification one immediately, just going to save me a bit of time, and x minus 2 squared. Okay, so this is going to be my expression for g of x. Now if I want to, I could immediately try and find out what a is. I can use the point that I have here, 0, 4. So I know that g of 0 is 4, and I'm showing you here that we don't even have to multiply this out if we want. We can find it straight away. Should be equal to 4. So a times 1 times minus 1 times 4 equals 4. So minus 4a is equal to 4, which means a is equal to minus 1. So that means that my function g of x is equal to minus 1 times x plus 1 times x minus 1 times x minus 2 squared. Let's just multiply these brackets out. So I'm going to start with the x minus 2 squared, x minus 2 minus 4x plus 4. Okay, and again, this is going to get fairly complicated straight through. Okay, if we want to, we can leave our answer in this format because we weren't actually asked to expand the brackets out fully, and it might be the best thing to do to avoid us making any mistakes. But we can leave our answer in that format. We don't actually have to multiply out the brackets fully. Okay, we're just given the expression. We're trying to give the polynomial in some sense. Okay, I'm going to make a mess of that if I start doing that now. So the idea is to pull the roots from the graph and then use the point that's been given to us to find that value of a. And that value of a is really important because it helps us to go from a polynomial to the polynomial. Until we've found out what a is, it's just a polynomial. Okay? Let's continue on and look at the last little question that we have here, which is a nice exam style question. So here we're given the graph of a polynomial, we're given a graph with 4 unknowns in its expression, and we're asked to find the value of each of these constants a, b, c, and d. So let's just look at the graph and see what it tells us. So I can see immediately I have a root here at minus 4. That's a distinct root. So that's a distinct root at x equals minus 4. I have a repeated root. So I have a repeated root at x equals minus 1. And I can see also that my graph crosses or has a y-intercept at x equals, or at y equals minus 2, or at the point 0, minus 2. So I have a repeated root at minus 1 and a distinct root at minus 4. So let's go from roots to factors. So my factors are x plus 4 and x plus 1 squared. Okay, that's my general expression for this polynomial. Looking at the shape of the polynomial as well, I am expecting that I will have a constant term at the front that is not just going to be 1. And the main reason I'm expecting that is my graph is starting up and going down the way. So I am expecting, so let's just write it down here, I am expecting to have a negative leading coefficient. And the reason I know that is because the right arm is pointing downwards. So that's kind of a reminder to me looking at this question that there is going to be some sort of constant part. We should always check for it, but in case we forget, we should know from looking at the graph that it's not just going to be these two factors multiplied by each other. So I have to also include my little expression there. And we can use a because that's going to be my leading coefficient there anyway. So let's just work it out. So f of x is a times x plus 4 times x plus 1 squared. Okay, I can use a. I could also use a different letter if we wanted to. It wouldn't make any difference. So in this case, let's just use one of the points that we have. So we know f of 0 is minus 2. So let's use that. So f of 0 is a times 0 plus 4 times 0 plus 1 squared, and it's equal to minus 2. So a times 4 times 1 equals minus 2. 4a equals minus 2, so a is minus a half. And as expected, we have a value for a there, and it's a negative value. So it's actually making my function kind of nearly flip from a standard cubic to a decreasing cubic. So going back to my original function here now, I can fill in my value for a of minus a half. I have x plus 4 and I have x plus 1 all squared. So I'm going to move forward to just evaluate some of the parts of this here. So x squared plus 2x plus 1 and x cubed plus 2x squared plus x plus 4x squared plus 8x plus 4. I'm going to just simplify all that before I multiply my half across. So plus 6x squared plus 9x plus 4. And I can finally just distribute that half across the minus half. It's going to change signs also. 9 over 2x minus 2. And lastly, I'm just going to finish by being really explicit about writing out what each point is. I should be okay at this point with having them all laid out, but just to make it really explicit, I'm going to just lay out exactly what the value is for each of my points there. So we can see how important it is to particularly know the root behavior. Okay, out of the two, the shape and the root behavior is the one that we've been using the most, recognizing your distinct roots and your repeated roots and bringing those together. The new thing that we've seen in those last few questions is this idea of this constant term, so that's really important, and this idea of it helping us to move from a polynomial, and how until we've evaluated a, it's just a polynomial, but moving to the polynomial in the question. Okay, also important generally though to know how the root behavior and the degree and the leading coefficient influence what your graph looks like and influence how the arms behave, how it's going, whether they're both going to point up, whether one's going to point down, which direction they are both going in, because that's going to help us then to draw those sketches, to make those sketches much more accurate. And particularly then when we move to functions, it helps us to kind of be sure if our function's correct. If we haven't, we'll be able to spot mistakes if we've made them, and just even generally being able to spot graphs if we're given them. So having a better understanding of what we think graphs should look like based on the information that we have. So it's all really, really important for you to kind of have a good idea with, and to have that sense of understanding of the roots and of the shape of your graphs.